Hey everybody, recording a quick video here on some trigonometry related to finding a point on a circle. One of the most common things that we're going to end up wanting to do in our apps and games is that we're going to start off here with the circle, and we're going to know kind of the center of the circle, and we're going to want some way to like generate a point on the edge of the circle. Okay, and maybe you actually want to generate a bunch of points around the edge of the circle, that are evenly spaced. There could be a lot of reasons that we want to do that, but very commonly the reason that we want to be able to generate points around a circle, is for like a lot of apps you've seen, like a wheel, it's like, oh, I want to change the volume, or I want to adjust the brightness or something like that. So having, marks that indicate, this is 20%, this is 30%, this is 40%, or something like that, can be very practical. But also we can use it to position elements, in a useful way around our screen. Right? So if I can calculate, if I want to arrange things in sort of a nice circle or an arc or something, if I have a way to basically generate a point on a circle exactly where I want, then I really have the ability to position things nicely. So that's what we're going to talk about today. So let's draw our circle back again, and let's think real quick, what are the parts of a, what are the things we know about a circle? We only need two things, according to Euclid, to define a circle. We need to know the center point, which I'm just going to call x center and y center. And then we need to know, what else do we know? Well, we know that there's a radius of some sort. Okay, like those are the two like really key aspects of any circle. Once we have that, we can put it anywhere we want. We just place the center. If we know how big it is, we can draw that around it, and that's really the essence of a circle. So if I'm trying to find this point out here, okay, doesn't really matter which one, they'll all be connected by the same radius. I'm just going to call this point xy. I want to find this point, or I want to generate this point. So I want to say, hey, what are the actual coordinates of that based on some information. So the first thing is with a lot of geometry problems, they sort of default into like, let's draw some triangles. It's a good strategy for almost any geometry you might want to do, is like, let's draw a few triangles there and see what happens. So if I come down here, I can sort of sketch the sides into a right triangle, which really is telling me how far away, this distance is how far away I am from the center on the x direction. This distance is how far I am, or I should say the vertical distance here. So I'm just going to call this, I don't know, we'll just call this V, and we'll call this one H. So V is the vertical distance here from our y center, and H is the horizontal distance from the x center. So I'm going to erase these V's and H because I'm going to call them something different here in a second. But the idea is if we could figure out those distances, then we'd be in great shape. So that means that on some level, we know that x is going to be, well, wherever we start at the center plus something that we got to figure out, and y is going to be, well, whatever's at the center plus something that we got to figure out. So we got to figure out what other information that we know. Well, if we made this triangle, and we think about this triangle, the thing we have kind of control over is that if we want to put a point somewhere sort of specifically around this thing, we can dictate which angle that we want to be in this corner, right? Because if we change the angle to 20 degrees or 30 degrees, that's going to result in a different XY pair. So now we have this kind of cool thing where here we have the ability to say, hey, look, let's set the angle, and then that's going to dictate the rest of the triangle, right? So we're going to go and we're going to do our nice SOHCAHTOA work. And SOHCAHTOA is going to let us say, hey, you know what, this is the opposite side to the angle. We'll let R be the hypotenuse, and we know that this is going to be the adjacent side to the angle. So what does our SOHCAHTOA say? Well, it says that I can use sine to find the opposite over the hypotenuse, right? So we know that sine of the angle equals opposite over the hypotenuse, which is just R. Okay, well, awesome. We want to know, well, how far is the opposite, or what the length of that is. Well, hey, we just multiply both sides by R. So we got R sine theta equals the opposite. Okay, so that means that, hey, look, our y coordinate is going to be y sub c plus R sine theta. So generically, we can plug in whatever radius we want, and we can plug the angle that we want it to be sort of, on the circle, and then that's going to generate the y. Similarly, cosine of the angle is what? It's the adjacent over the hypotenuse. So that gives us our cosine theta is equal to the adjacent. Awesome. So that means this is going to be our cosine theta. So these are going to be our two really important formulas for deriving that point on the line. So you notice that we've made them nice and generic, which is going to be really useful. We're going to be able to feed in specific values of theta. So let's think about that for a second, and we got to think about, well, how are we going to think about angles on the circle? So I'm going to leave that there. I'm going to redraw this picture for a second. So I'm going to erase these guys. And so when we're thinking about how to redraw or reconsider this theta, okay, the tempting thing is to put in 360 degrees, which works like sort of in generic and math class, that's great. But the computer doesn't like degrees. The computer likes to work in radians. So we have to think a little bit about what radians and degrees are. So if I draw my circle again, we know that there's 360 degrees in the circle. Okay, but the computer likes radians, and so we got to think about, well, what are radians? If you don't know what radians are, if I have a circle and I put a radius here, well, what's the circumference? The circumference is 2 pi r, right? I go 2 pi times the radius of the circle. And if you've never really thought about that, what that really means is if you take this center radius here, and I was able to sort of bend it around the edge of the circle, I would be able to take this and, sort of go dun, 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 dun. And if I like cut little pieces of string and I set it around, I'd be able to go 2 pi times around the circle, which is, a little more than 6. So basically it takes 6 of these segments to sort of lay out around a perfect circle. So that's maybe surprising, but it's certainly one way to think about it, because really what that lets us do is that when we think about angles, okay, this is some angle here, right? This guy right here, and it's a way to measure, and it doesn't tell you very much about the size of the circle, right? Because I could have a teeny tiny circle like this, or I could have this big circle, and if I said, 30 degrees, well, I would know that that was a proportion of the circle, but I wouldn't really know, how big that particular circle it is. Similarly, if I wanted to know how 30 degrees translated into a distance along this, I'd have to set up a ratio, right? So I'd be like, oh, well, let's say it was 36 degrees. Oh, that's 1/10 of the circle. Now I got to find the circumference, and now I got to say, hey, that's, do that multiplication, found that ratio. Well, the other way to think about distance around the circle is we could say, hey, look, this is another perfectly reasonable consideration of like what portion of the circle you have, right? And we know that because of how our formula works, because it's 2 pi times the radius, regardless of the radius, there's 2 pi of whatever around the circle, right? So in that case, that's what we get by the idea of radians. There's 2 pi of the radius around the circle. So I can now think of, oh, this little section, if it was, 36 degrees, I could say, hey, that's 2 pi over, in this case, it's a 10th, divided by 10. Hey, that's pi over 5. Pi over 5 represents a 10th of the way around the circle. But the other part about this is it's already, like, we're thinking about it in terms of a distance. So as soon as I multiply this by the radius, I actually know how far this distance is. So that's why a lot of computer folk and stuff like it. It's a little different than your average deal. So anyways, why is this important? It's because we got to convert between radians and degrees fairly often. If there's 360 degrees and there are 2 pi radians, hey, we got to be able to set up ratios. So if I want to go from radians to degrees, then I'm going to be doing 180 over pi, right? Because 360 over 2 pi. Or I'm going to be doing pi over 180. So this ends up, I want to go 2 radians, 2 rads, and this is going to be 2 degrees. Okay, so hopefully that will cover the math you guys need for this packet, and we'll be in good shape. Cheers. Have a nice day.